I'll read out the question, but it's on page 190 of your books anyway. We're now going to apply our knowledge of that rule of logs in our log tables. So we've only really just been looking at one rule, and it's been this one here. So we want to be able to go in and out of logs. Logs are all about missing powers. So I'm going to have a read of the question here, and if at any stage, I've had something missing, well, really that's algebra. Now, if it happens to be a missing power, I might use logs, but I'm trying to use my algebra always to figure this stuff out. So real life question, we have a population of bacteria grows exponentially according to this model. All it means is there's a formula. So they've obviously watched bacteria growing previously in an experiment, and they've tried to come up with some sort of formula that will predict how many cells of bacteria or whatever it is will be present in 2 minutes time, in 10 minutes time, in an hour's time. And if they can do this, well, then they can predict a lot of things to do with growing bacteria or decaying. So they've said here that the population of the bacteria is equal to 600 times E. So E is a very common number in nature. If you go to your calculator, you'll find what that number is by, it's down here for me, it's the number 2.7182818828 and so on. And it's just a number, like pi, never ending number, gets its own name so that we can talk about it without saying the number every single time. And then it's that number to the power of 0.1144 times t, where t is the time measured in minutes. So for something to grow exponentially means it's going to grow like double or treble, or it'll grow very, very quickly, usually. And I'm going to have a go at what is the size of the population at time equals 0. So it's always good it's always good for us to notice the time at the time is 0 at the beginning of an experiment. So what is happening with my experiment, or in this situation, with my bacteria at the start of the experiment? Well, population is equal to, and this is for my model, 600 e to the power of 0.1144 t. The time is in minutes, and at the moment they want me to talk about 0 minutes. Well, if I want the population at time equals 0, then this is what I'm looking at. So anything times 0 is 0. Anything to the power of 0, so it's just e to the power of 0, otherwise there'll be brackets around the 600. So anything to the power of 0 is 1. So that's 600 times 1, which is 600. So the population of the bacteria at the very start is 600. Now, they've asked me in the second part what happens as it grows exponentially, and the population, what will the population be at time equals 10? So after 10 minutes, what do I expect to happen? Well, I put in 0 when it was 0 minutes, so now I'm going to put in 10 when it's 10 minutes. Again, I should just be pretty straightforward. I should be able to throw that into the calculator, and so that's 600 by e to the power of 0.1144 times 10. And I get 1883.5, Now, have they asked me to round off? If they haven't, I'm just gonna give the full answer and then just say approximately 1,884. They haven't asked me to round, so I'm going to give the full answer and then I can say approximately 1,884. Find the nearest minute. Okay, well this time t is missing. The time at which the population will have grown to 6,000. It is possible to guess and check here, but we now know the population is 6,000. So instead of the P, I'm putting in the 6,000. Now you could guess and check, as I said, but I would try and do my maths. So firstly, what's going on here? Well, that has this power and T is caught up here. So I'm going to always try and isolate my missing number. So I'm going to divide by 600 in order to try and make this look a bit simpler. When I divide by 600, I end up with 10 is equal to, that's gone, e to the power of 0.1144 to the power t. Maybe I guess and check here because I'm stuck. I would prefer to use my log tables. Because I have a missing power, I know I can use logs here to try and figure this out. But in order to use logs, I need to try and be able to use this rule here. So I need to try and write what's here like this and hopefully just put that into my calculator. So what's my base number? It looks like E. So if I write this as log in the base E of 10 is equal to 0.1144t. Now, put this into my calculator. Log base E 10 so I'm after throwing this into the calculator. 2.302585093 is equal to 0.1144 times t. Get the t all by itself now by dividing by 0.1144, and we have 20.127 is the time. And I think they said round off to the nearest minute, which they did. So I'll round off to the nearest minute, that's about 20 minutes. So in 20 minutes, the bacteria will be at 6,000.